Our universe holds families of 6 stars dancing in perfect gravitational harmony. These sextuple star systems defy our basic understanding of how stars live and interact. By the end of this journey, you will know 25 of the most bizarre secrets astronomers have uncovered about them. We will explore worlds with multiple suns and stars that share a single atmosphere. How stable can a cosmic neighborhood be when 6 suns pull at each other constantly? What does that reveal about the nature of our own solitary solar system? High in the winter sky, the twin stars of Gemini have watched over humanity for millennia. One of them, Castor, shines with a steady, singular light to the naked eye, a beacon of constancy. Yet this constancy is a magnificent illusion. Castor is not one star, but a stunning cosmic family of 6. The unraveling of its true nature began not with advanced technology, but with the sharp eye of astronomer William Herschel in the late 18th century. He was the first to notice something peculiar, that Castor was not a single point of light but 2 stars orbiting one another. This was the first crack in the celestial facade. For over a century, Castor was known as a brilliant binary, a pair of suns locked in a gravitational dance, but the mystery was only beginning to deepen. Modern astronomy, armed with the powerful tools of spectroscopy and interferometry, peered closer. Spectroscopy splits the light from a star, revealing its chemical fingerprints and, crucially, its motion. When a star moves toward us, its light shifts to the blue end of the spectrum, and when it moves away, it shifts to red. By studying these shifts, astronomers discovered that each of the 2 stars Herschel saw was itself not a single star, but a pair of stars orbiting so close together that no telescope could separate them. The simple binary was now a system of 4, and the final piece of the puzzle lay even farther out. A third pair of stars, much fainter and redder, was found in a wide, slow orbit around the entire inner group. Castor was a sextuple system, a cosmic nest of 3 binary pairs. The orbital dance is a masterpiece of gravitational choreography. The 2 brightest binary pairs whirl around each other in an orbit that takes nearly 450 years to complete. Meanwhile, the stars within each of those binaries are themselves spinning around one another in a matter of days. Holding this entire intricate dance at a respectful distance is the 3rd binary pair, tracing a vast, lazy circle around its brilliant siblings. The discovery of Castor's 6-fold heart fundamentally changed our perspective. It proved that star systems of such staggering complexity were not just theoretical possibilities, they were real, and they were shining in our own galactic neighborhood. This revelation forces a profound question. If a star as familiar and bright as Castor holds such a secret, what other multiplicities are hiding in plain sight, waiting for their stories to be told? While Castor revealed its secrets over centuries, a far more intricate cosmic dance was recently spotted in a single, brilliant flash of data. Meet TESS 168789840, a sextuple star system that redefines the very idea of a crowded neighborhood. Discovered by NASA's TESS mission, this system is not just 6 stars. It is 3 pairs of eclipsing-binaries, all bound together in an astonishingly tight gravitational embrace. From our vantage point, we are looking directly into its orbital plane, giving us a front-row seat to a constant celestial ballet. Stars in each pair regularly pass in front of one another, causing their combined light to rhythmically dip and brighten in a predictable, complex pattern. This is not a slow, stately waltz like Castor's, but a frantic, close-quarters tango. The sheer proximity of these stars is what baffles astronomers. In such a cramped gravitational environment, you would expect chaos, a violent scattering that tears the system apart within a short cosmic time frame. Yet the evidence suggests TESS 168789840 has been performing this dance for billions of years. Its stability is a profound puzzle, a delicate balance of forces that seems to defy the odds. For scientists, these frequent eclipses are a scientific goldmine. Each time one star transits another, it acts like a natural diagnostic tool. The precise changes in light reveal the star's exact sizes, masses, and temperatures with a level of accuracy that is nearly impossible to achieve by any other means. It is as if the universe itself designed the perfect laboratory for studying stellar physics. How can such a complex system remain so perfectly tuned for so long? And what does its enduring harmony teach us about the fundamental rules governing all stars? The dance of six stars can become so intimate that two partners essentially merge into a single, shimmering entity. Within the complex architecture of systems like HD 139691, astronomers have found binary pairs in a state of extreme closeness known as overcontact. These are not just stars orbiting nearby, they are stars that physically touch, their outer atmospheres blending into a single, common envelope of superheated gas. Imagine two spheres of fire pressed so tightly together that they deform into a single, peanut-shaped structure, endlessly swirling with shared stellar material. This creates a system of constant exchange where hydrogen fuel and other elements flow directly from one star to its companion. This profound connection generates ferocious magnetic fields and can trigger unpredictable flares, making these binaries some of the most volatile and active objects in the cosmos. The ultimate fate of such a pair is a spectacular merger. Over millions of years, the relentless gravitational embrace and the friction of their shared atmosphere causes the two stars to spiral inward, finally collapsing into one massive, rapidly spinning star. This newborn star, often called a blue straggler, appears unnaturally young and brilliant compared to its stellar siblings. The existence of these touching stars within a sextuple system shatters the classic image of stars as isolated, solitary spheres. It reveals that in the crowded gravitational neighborhoods of multiple star systems, the lines between individual celestial bodies can become permanently blurred. What does it mean for our understanding of a star's life when its very identity can be consumed by its closest partner? This delicate gravitational ballet is made possible by one of the most fundamental and strange principles of these systems, a strict hierarchy of orbits. Sextuple stars do not simply swarm around a common center like a chaotic hive of bees. Instead, they organize themselves in a remarkably structured way, most often in what astronomers call a 2+2+2 configuration. Picture our solar system, but instead of one sun at the center, imagine a pair of stars orbiting each other so closely they are practically a single unit. Now, imagine another identical pair of stars orbiting the first pair from a greater distance. Finally, envision a third binary pair tracing an even wider, slower circle around the entire inner group. You have just visualized a stable sextuple system. It is a cosmic nesting doll of gravitational influence. The tightest, fastest orbits are at the very core, with each subsequent pair moving in a progressively larger and slower dance. This layered structure is not just for show, it is the key to survival. The immense distances between these nested orbits act as a buffer, smoothing out the violent gravitational tugs that would otherwise tear the system apart. Computer simulations paint a stark picture of what happens without this precise order. If all six stars were to orbit on similar paths or in a single, flat plane, their interactions would quickly become a chaotic gravitational free-for-all. Stars would be slingshotted into interstellar space, or worse, they would be drawn into catastrophic, system-shattering collisions. The fact that we observe so many of these hierarchical systems tells us something profound. This specific, orderly arrangement is not a cosmic coincidence, it is a necessity. It is the only way for a family of six suns to find a lasting peace in the violent theater of space. So the next time you look up at a seemingly simple point of light, remember that it might not be a single star, but a carefully structured celestial empire, governed by rules of order that allow for its very existence. Such gravitational order raises an even more tantalizing prospect. Could planets actually form and survive within the chaotic light of six suns? The very idea seems to defy physics, as a planet trying to coalesce from a disk of dust and gas would be relentlessly tugged and torn by six competing gravitational fields. Yet, against all odds, astronomers theorize that worlds could exist in these systems, but only by finding a very specific cosmic parking spot. The most stable solution is for a planet to orbit at an immense distance, so far out that the entire sextuple system appears from its perspective as a single, combined gravitational point. From this remote vantage, the planet would trace a slow, grand circle around all six of its suns. Alternatively, a world could huddle very close to one of the inner binary pairs, trapped in a tight orbit where the gravitational pull of its two host stars dominates, shielding it from the disruptive influence of the other, more distant stars. Imagine standing on the surface of such a world. Your sky would be a spectacle of impossible geometry. Multiple suns, each perhaps a different hue of orange, white, or red, would trace complex paths overhead. Some would set while others rose, casting multiple, ever-shifting shadows. There might be periods where several suns are above the horizon at once, creating a day of overwhelming brightness, and other times when only the faintest red dwarf is visible, offering a perpetual twilight dusk. True, deep darkness might be a rarity, a fleeting moment unknown to that world's inhabitants. The existence of such a planet would be the ultimate testament to cosmic stability, a world born from chaos and cradled by a perfect gravitational balance. While a planet in a mature sextuple system is a triumph of stability, the youth of such a system is a scene of pure chaos. HD 98800 is a stellar nursery of six stars, a place where the very process of planet birth is being stress-tested by gravitational turmoil. This system is so young that it is not yet a single, unified sextuple, but rather two separate quadruple systems locked in a wide, lazy orbit around each other, earning it a place among these complex families. The true wonder lies around two of its inner binary pairs, where astronomers have spotted vast, swirling disks of dust and gas. These are not the serene, organized rings of Saturn, but violent construction zones where the raw materials for planets are colliding and coalescing. Seeing such active, planet-forming debris disks in a system with so many competing stars is deeply strange. In a solitary system like our own, a protoplanetary disk can settle into a calm, flat plane. Here, the gravitational influence of the other stellar members is relentless. Observations from the powerful LM telescope array reveal these disks are not flat at all. They are warped, twisted, and show distinct gaps and rings, their structures carved and sculpted by the constant gravitational tugs of their stellar siblings. It is as if you are trying to build a house of cards in the middle of a busy highway. The very forces that provide the material for new worlds are also the forces that threaten to tear them apart before they can fully form. This creates a cosmic race against time. Can planetesimals clump together fast enough to form the core of a new world before a passing star's gravity scatters the dust into oblivion? The warped disks of HD 98800 are a live demonstration of this brutal selection process, showing us that in a system with six suns, the path to planetary existence is the ultimate cosmic obstacle course. The data from these crowded stellar families paints a picture not with images but with light. The combined glow of a sextuple system, when plotted over time, creates a graph called a light curve. For a single star, this line would be almost perfectly flat, but for a system like TIC 168789840, the light curve is a wild, scribbled signature of celestial motion. It records a cascade of eclipses where the rhythm of one binary pair's dance is perpetually interrupted by the transits of another. Imagine trying to listen to three different songs playing at the same time, each with its own distinct beat. The result is a chaotic symphony of dips and peaks. One star in the closest binary may pass in front of its partner, causing a deep, brief dimming. Before that event even finishes, a star from the second pair might begin its own transit, creating a secondary, overlapping dip in brightness. The overall pattern is a complex tapestry of shadows, predictable in its components yet bewildering in its combined complexity. Astronomers have become masters of this stellar cryptography. They do not just see the chaos, they see the clockwork within it. Each specific dip reveals profound secrets. The depth of the dimming tells them the relative sizes of the stars involved. A very deep eclipse means a large star is being blocked by its companion. The duration of the dip reveals the orbital speed and the distance between the stellar partners. The shape of the curve, whether it is sharp or rounded, can even indicate if the stars are distorted into egg shapes by their mutual gravitational pull. This is how a flickering point of light transforms into a detailed astrophysical dossier. The true strangeness emerges when the predicted pattern of dips does not match the observed data. A tiny, unexplained flicker buried within the tangled web of light can be the only clue pointing to a previously hidden stellar component, a faint, distant star whose presence was otherwise completely masked by its brighter siblings. Untangling this web requires more than human intuition. It demands powerful algorithms that can sift through thousands of data points, testing millions of orbital configurations to find the one perfect model that explains every single dip and flash. The light curve is more than a graph. It is the system's heartbeat, and its irregular rhythm holds the keys to its deepest mysteries. Hierarchy is the rule for survival in these complex families, but some systems dare to break it. Deep within the crowded stellar nurseries of our galaxy, astronomers have found the chaotic hearts of trapezium-like sextuple systems. They are the rebels of the multiple-star world, defying the stable, nested order that keeps other families together. A classic trapezium, like the brilliant quartet at the core of the Orion Nebula, is a group of young, massive stars all orbiting in a tight, non-hierarchical cluster. Their gravitational pulls are roughly equal, creating a volatile environment where no single pair dominates. Now, imagine that same chaotic principle applied to the core of a sextuple system. Instead of three neatly separated binary pairs, you find a tight knot of 4, 5, or even all 6 stars moving in a complex, chaotic dance. This configuration is incredibly rare and profoundly unstable. In such a system, the gravitational forces are a tangled web. A star is pulled almost equally by all its neighbors, leading to unpredictable orbits that are constantly shifting. These are not the clean, elliptical paths of a hierarchical system, but wild, looping trajectories that resemble a swarm of bees more than a formal dance. On cosmic timescales, this chaos is fleeting. Such a system cannot last for billions of years. The relentless gravitational interactions will inevitably slingshot one or more stars out into the void of interstellar space, breaking the family apart in a violent act of cosmic ejection. The very existence of these trapezium-like sextuple systems is therefore a profound puzzle. Their presence suggests one of two strange possibilities. The first is that we are catching them at a moment of incredible rarity, witnessing the brief, fiery youth of a stellar family that is destined for a rapid and dramatic divorce. They are stellar infants still settling from the turbulent cloud of gas that gave them birth, and we are seeing them just before they fly apart. The second, more intriguing possibility is that there are unknown stabilizing factors at play. Perhaps subtle resonances between the orbits or the presence of faint, unseen masses are providing just enough gravitational glue to hold the chaos at bay for longer than our current models predict. Either way, these chaotic systems are a direct challenge to our understanding of stellar dynamics, forcing us to ask if our models of gravity are complete, or if the universe still holds secrets about how stars can temporarily coexist in a state of beautiful, dangerous turmoil. The same gravitational turmoil that creates trapezium chaos can also forge cosmic projectiles. Some of the galaxy's most solitary and speed-blurred stars, known as runaway stars, may carry the scars of a violent sextuple system breakup. These stellar outcasts are not born flying solo. They are violently ejected from their crowded homes. The mechanism is a gravitational slingshot, a celestial billiard shot of incredible precision and power. In an unstable system, a close encounter between two or more stars can transfer a massive amount of orbital energy to one of them. Instead of settling into a new, stable path, that star is flung away from the group at a staggering velocity, often exceeding the escape speed of the galaxy itself. It becomes a hypervelocity star, a lone wanderer on an irreversible journey into the intergalactic void. Astronomers act as cosmic detectives when they find these runaways. The primary clue is their incredible speed and trajectory. By tracing the path of a runaway star backward through the galaxy, they can sometimes point directly to its origin, a young, dense star cluster or a known multiple system that shows signs of recent dynamical upheaval. One famous candidate is a star known as HE 0437-5439, observed rocketing out of the Large Magellanic Cloud. Its speed, over 750 kilometers per second, is so great that it will inevitably leave its galaxy behind. The most likely explanation for such an extreme velocity is a multi-body gravitational encounter, possibly the final, explosive moment when a complex system like a sextuple could no longer hold itself together. This discovery forges a direct link between the strange, small-scale dynamics of multiple star families and the large-scale population of the galactic halo with fast-moving, lonely stars. Each runaway is a potential piece of forensic evidence, a silent witness to a catastrophic gravitational event that happened millions of years ago. What other solitary lights in our night sky are actually refugees from a forgotten stellar family that tore itself apart? The life of a star in a family of 6 is never its own. Isolated stars like our Sun follow a predictable, solitary path from birth to death, governed almost exclusively by their initial mass. But place a star in the relentless gravitational embrace of 5 siblings, and its evolutionary journey becomes a shared, often bizarre experience. The most intimate alteration occurs within tight binary pairs, where 2 stars orbit so closely that they can literally siphon material from one another. This process of mass transfer can completely rewrite a star's destiny. A smaller, aging star might have its outer layers stripped away by a more massive companion, prematurely exposing its hot core and cutting its life short. Conversely, a star nearing the end of its life could receive a massive infusion of fresh hydrogen fuel from its partner. This stolen material acts like a cosmic fountain of youth, reigniting nuclear fusion with a fury and causing the star to balloon in size and luminosity. It becomes a blue straggler, a stellar imposter that appears unnaturally young and vibrant compared to its true-aged siblings, a direct contradiction to everything we thought we knew about stellar aging timelines. The ultimate communal event, however, is a supernova. In a system of 6 stars, the death of one member is not a quiet affair, it is a family-wide catastrophe. When a massive star exhausts its fuel and collapses, the resulting supernova explosion is rarely perfectly symmetrical. This asymmetry gives the dying stellar core, now a neutron star or black hole, a powerful kick, launching it through space at hundreds of kilometers per second. In a delicately balanced sextuple system, this supernova kick is like a hammer blow to a precision clockwork. The sudden, violent loss of mass from the exploding star and the rocket-like recoil imparted to its remnant can instantly destabilize the entire gravitational hierarchy. Orbits that were stable for billions of years are suddenly warped and stretched. Stars can be flung into new, chaotic paths, or the entire system might be torn apart, scattering its members across the galaxy. This leads to an even more staggering possibility, a chain reaction of stellar death. If the stars in the system are all of similar large mass, the shockwave and radiation from one supernova could theoretically trigger the collapse of another unstable sibling. The system could experience multiple supernovae in a rapid cosmic domino effect, a series of blasts that would utterly obliterate any fragile planetary systems and leave behind a chaotic graveyard of stellar remnants. This reveals the core discovery that in these crowded neighborhoods, stellar evolution is not a series of isolated life cycles. It is a tangled, interdependent web where one star's birth, life, and violent death can directly script the fate of the other five. The silent waltz of six stars does more than paint the sky with multiple suns. It literally bends the fabric of the universe. When the members of a sextuple system are not ordinary stars but the incredibly dense remnants of stellar death, like neutron stars or white dwarfs, the entire system transforms into a relentless gravitational wave factory. These are not pools of calm water, but a churning ocean of spacetime itself. According to Einstein's theory of general relativity, any massive object in accelerated motion creates ripples in spacetime, much like a spinning propeller churns the water around it. For most objects, these ripples are vanishingly small, but pack the mass of an entire star into a city-sized sphere of pure neutronium and spin it around a companion at dizzying speeds, and the effect becomes profound. Each tight binary pair in such a system would be a powerful, steady source of these spacetime ripples, bleeding away orbital energy and slowly spiraling inward toward an eventual merger. Now amplify that phenomenon by 3. A sextuple system with 3 interacting pairs of these ultra-dense objects would not produce a simple, clean signal. Instead, it would generate a complex, humming chord in the fabric of spacetime, a superposition of multiple frequencies all interfering with one another. It would be a gravitational symphony, with each binary pair contributing its own distinct note to a cosmic cacophony. While no observatory has yet detected the unmistakable fingerprint of a sextuple gravitational wave source, sophisticated computer simulations reveal exactly what to listen for. The signal would be a tangled web of frequencies, its modulations telling the precise story of the system's hierarchical structure and the masses of its incredible constituents. This makes these systems a primary target for the next generation of observatories, like the space-based LIS mission. The profound strangeness is that these chaotic stellar families become nature's own perfect laboratories. They allow us to test the predictions of general relativity in a regime of gravity so extreme that it is impossible to replicate anywhere else in the universe. We could witness how spacetime itself behaves when it is stretched and squeezed not by 1 or 2, but by 6 incredibly dense masses in a frantic, intertwined dance. What new rules of physics might we uncover by listening to the hidden music of a system that warps the very stage upon which it dances? A star's light can tell a story of cosmic violence. When astronomers point their spectrographs at the members of a sextuple system, they are not just measuring temperature, they are reading a chemical autobiography written in the star's outer layers. Normally, a star's atmosphere reflects the composition of the primordial cloud from which it was born, but sometimes they find a star with a deeply strange chemical signature, one that betrays a history of stellar cannibalism. This forensic evidence comes from the most intimate binary pairs, where 2 stars orbit in a tight gravitational embrace. If one star expands as it ages, its outer layers can be pulled directly onto the surface of its companion. This transferred material is not pristine hydrogen. It is often heavily enriched with the byproducts of nuclear fusion from the donor star's core, elements like carbon, nitrogen, and oxygen. The receiving star becomes chemically polluted, its surface permanently contaminated with the guts of its partner. An even more dramatic chemical overhaul happens during a full merger. When 2 stars spiral together and coalesce, their internal materials are violently churned and mixed. The resulting single star bears the chemical imprint of both its progenitors, a hybrid object that should not exist according to standard models of stellar evolution. Finding one of these chemically anomalous stars nestled within a stable sextuple system is like finding a single fingerprint at a crime scene. It is direct, undeniable proof that a violent transformational event occurred in this family's past. The system may look calm and orderly now, but its light reveals a secret history, a moment of cosmic consumption that forever altered the identity of one of its members and left a permanent chemical scar as the only evidence. This recurring cataclysm reveals a star that refuses to die. Deep within the gravitational web of a sextuple system, a white dwarf can become a cosmic zombie, a stellar corpse that periodically returns to violent life. This white dwarf is the dense, Earth-sized core of a sun-like star that has exhausted its fuel and died, but its death is not permanent. If it has a close stellar companion, it can use its immense gravity to slowly steal hydrogen gas from that star's outer layers. This stolen material accumulates on the white dwarf's incredibly hot surface, building up for decades or even centuries. Eventually, the pressure and temperature at the base of this hydrogen layer become so extreme that nuclear fusion violently reignites. The entire surface of the white dwarf detonates in a blinding flash known as a nova. The star flares to life, increasing its brightness by tens of thousands of times in a matter of hours before slowly fading back into its dormant state. In a solitary binary, this cycle might follow a predictable, internal clock dictated only by the two stars involved. But place this volatile pair within a sextuple family and the entire dynamic changes. The gravitational pulls from the other four stars act like constant, subtle tugs on the stream of stolen material. They can squeeze the flow of gas, making it more efficient and triggering more frequent eruptions. Or they can stretch and disrupt the stream, delaying the inevitable explosion. The strange discovery here is that this external orchestration can create a clockwork nova. The system's complex gravitational rhythms can actually synchronize the eruption cycle, forcing it into a precise, predictable timetable that is set not by the binary pair alone, but by the grand orbital dance of all six stars. This means the entire stellar family, working in concert, dictates the timing of one member's repeated resurrection. How do we know such a precise cosmic clock exists? Astronomers have observed recurrent nova in other systems, their eruptions documented over centuries. Finding one within a confirmed sextuple system would be the ultimate proof, a stellar zombie whose awakening is conducted by the invisible hands of its five siblings. The orbits of the visible stars sometimes tell a story the light cannot. Astronomers meticulously charting the paths of the six known members in a system will occasionally find a persistent wobble, a tiny rhythmic drift in a star's position that the gravitational pull of its five siblings simply cannot account for. This anomaly points to an unseen dancer in the celestial ballet, a dark companion whose presence is felt only through its relentless gravitational tug. These hidden masses could be almost anything. They might be failed stars known as brown dwarfs, objects too massive to be planets, but not massive enough to ignite sustained nuclear fusion in their cores. They could be rogue planets, Jupiter-sized worlds ejected from their original orbits and now drifting freely within the gravitational confines of the system. Or, in the most extreme and thrilling scenario, they could be stellar mass black holes, the invisible remnants of a massive star that died in a supernova long ago, leaving behind only its gravitational shadow. Unmasking these phantoms is a painstaking process of elimination. Scientists build incredibly precise computer models of the system, inputting the known masses and orbits of all six stars. When the model's prediction fails to match the actual observed motion, the hunt begins. They must calculate the precise mass and orbit of an unseen object that would perfectly explain the discrepancy. It is celestial detective work of the highest order, where the crime is a gravitational disturbance and the only clue is a star that refuses to follow its predicted path. This discovery profoundly changes our understanding of these stellar families. A sextuple system is already a cosmic crowd, but the confirmed presence of a dark companion reveals it is even more densely populated than we thought. The family portrait is incomplete, with one or more members lurking just outside the frame, their silent gravity orchestrating the dance from the shadows. What other secrets are these systems keeping, and how many invisible giants are quietly shaping the destinies of the stars we can see? This gravitational lockstep is not a product of chance, but a deep mathematical harmony. Within the most enduring sextuple systems, astronomers have detected a literal music of the spheres, where the orbits of the different binary pairs are synchronized in perfect clockwork ratios. This phenomenon is known as orbital resonance. Imagine the inner binary pair completes its tight, frantic dance exactly 3 times for every single, slower orbit of the middle pair. Or the outermost pair takes precisely twice as long to circle the system as the middle pair does. These are not approximate timings, but precise, mathematical integers governing the celestial dance. This gravitational synchronization acts as the system's ultimate stabilizer. When the orbiting pairs fall into these resonant rhythms, their gravitational tugs become predictable and reinforcing, rather than chaotic and disruptive. Each time a pair returns to a specific point in its orbit, it feels a consistent, gentle pull from its siblings, a rhythmic nudge that keeps it perfectly on track. This repeated, coordinated interaction prevents the orbits from drifting into dangerous, overlapping paths that would lead to gravitational slingshots or collisions. The profound strangeness of this discovery is that it reveals a self-organizing principle on a cosmic scale. This perfect harmony was not programmed into the system from the beginning. Instead, it emerged naturally from the initial chaos of its birth. Over millions of years, the relentless and initially messy gravitational interactions between the pairs slowly sculpted their orbits, tuning them like the strings of a celestial instrument until they settled into these stable, resonant frequencies. It is a delicate balance born from turbulence, a natural order that the system discovered for itself to ensure its own long-term survival. How many other complex stellar families are quietly humming these same gravitational melodies, their stability guaranteed by a hidden, mathematical music we are only just beginning to hear? The star Nu Scorpii shines in the constellation Scorpius as a single, steady point of light, a testament to the limitations of our own eyes. Its true nature began to surface in the early 19th century, when astronomers with powerful telescopes noticed it was not one star but 2. This visual binary, Nu Scorpii A and B, separated by a generous swath of space, became the first layer of a deeply nested mystery. For nearly a century, that was the accepted view, a simple pair of suns. The next breakthrough came with the advent of spectroscopy, which revealed that both of these stars were themselves hiding a secret. The light from Nu Scorpii A, when split into its rainbow of colors, showed a telltale doubling of its spectral lines, shifting back and forth in a rhythmic pattern. This was the unmistakable signature of a spectroscopic binary, 2 stars orbiting so incredibly close together that no telescope could ever hope to separate them. The same phenomenon was discovered for Nu Scorpii B. In an instant, the simple binary became a system of 4 stars, but the unraveling was not yet complete. Further painstaking analysis of Nu Scorpii A's complex light revealed a faint third set of spectral lines dancing to their own, much faster rhythm. This was a 5th star, locked in an incredibly tight orbit with the primary star of the inner binary. This tiny, close-knit triplet formed the heart of the system, a stellar unit within a unit. Officially, Nu Scorpii is classified as a quintuple system, a family of 5. Yet its very existence screams of a deeper truth about stellar multiplicity. If a system can naturally form with such intricate, layered complexity, with a tight triple at its core and wider binaries surrounding it, then the leap to a full sextuple system requires the addition of just one more star, perhaps in a wider orbit still waiting to be found. New Scorpii stands as a brilliant, nearby example of how the universe builds its stellar families not as simple pairs, but as intricate nests of gravitational relationships. It proves that the potential for a sextuple system is often written in the layered architecture of its slightly simpler cousins, hiding in plain sight behind a veil of seemingly singular light. These intricate families of six do not exist in isolation. They are often found within the bustling stellar metropolises of young, open clusters, where their dramatic lives can reshape the entire neighborhood. The prevailing theory for their birth is as elegant as it is chaotic. A single, exceptionally dense core within a vast cloud of gas and dust begins to collapse under its own gravity. But instead of fragmenting into just 2 or 3 pieces, this core shatters into 6 distinct knots, each destined to become a star. This initial fragmentation is a delicate balancing act, requiring the perfect conditions of temperature, density, and rotation to create a stable hierarchy right from the start. Once born, however, these sextuple systems become gravitational heavyweights within the cluster. Their complex multi-body dynamics act like a powerful engine, driving the cluster's evolution through a series of gravitational encounters. When a lone star passes too close to a sextuple system, the encounter is rarely a simple deflection. The intruding star can be captured into a temporary, chaotic dance, receiving a massive gravitational slingshot that flings it out of the cluster entirely, becoming a runaway star. Alternatively, the sextuple system itself can be jolted, its orbits rearranged or even broken apart by the intruder's gravity. This constant gravitational pruning has a profound effect. It helps to strip away the cluster's lower mass members, slowly evaporating it over time and determining its ultimate lifespan. Furthermore, the exotic stellar products forged within these systems, like blue stragglers from stellar mergers or chemically polluted stars from mass transfer, are then released back into the cluster population. The sextuple system effectively seeds its surroundings with these strange stellar hybrids, permanently altering the chemical and demographic makeup of its birthplace. Far from being mere celestial curiosities, these families of 6 are potent agents of change, their turbulent lives writing the very history of the star clusters they call home. A star's magnetic fury can be ignited by the pull of its closest partner. Within the tight binary hearts of sextuple systems, astronomers have measured a strange and persistent rage. The chromosphere, a star's outer atmosphere, is typically a seething but predictable layer of superheated gas. Yet in these gravitationally locked pairs, that layer becomes a storm of magnetic violence. It burns hotter and churns with far greater turbulence than the chromosphere of any isolated star of the same type. This ferocious activity announces itself not in visible light, but in the high-energy realms of the spectrum. These stars blaze with intense, unexpected brilliance in X-ray and ultraviolet light, shining far brighter than they have any right to. The cause is not something within the star itself, but a force imposed upon it from the outside. It is the relentless gravitational grip of its binary companion. As the 2 stars whirl around each other in their incredibly close orbit, their mutual tidal forces act like a cosmic brake and accelerator simultaneously. They lock the star's rotation, forcing them to spin in perfect time with their orbital period. This rapid, synchronized spinning acts like a dynamo, supercharging the churning plasma deep within the stars and amplifying their magnetic fields to extraordinary strength. The discovery here is profound. A star's magnetic personality, long thought to be a simple function of its mass and age, is not its own. It is a shared property, a collaborative fire stoked by the relentless gravitational tug of a partner. A star that would have been magnetically quiet if born alone becomes a raging beacon of high-energy light simply because it lives its life in an intimate, tidal embrace. This means that from our distant vantage point, the heightened X-ray glow of a tight binary is more than just a curious reading. It is a direct signal, a testament to the invisible forces that bind these stars together, and a clear warning of the stormy relationship playing out within the calm facade of the larger stellar family. For hundreds of years, the true nature of these stellar families was a perfect cosmic secret. The most powerful telescopes on Earth could only see them as solitary, unwavering points of light, their intricate dances completely invisible to our eyes. The revelation of their sixfold hearts did not come from a bigger lens, but from a deeper way of seeing. The key was high-resolution spectroscopy, which could detect the subtle, rhythmic wobble in a star's light caused by the unseen gravitational tug of its companions. Later, techniques like speckle interferometry allowed astronomers to effectively cancel out the blurring of our atmosphere, splitting that single point of light into its distinct stellar components for the very first time. This technological leap was like giving humanity a new sense, one that could perceive the gravitational bonds between stars rather than just their light. The fundamental strangeness here is that the universe's complexity is often an invisible layer, a hidden reality waiting just beyond the limits of our perception. It forces a humbling question. We now know of a handful of these sextuple systems, but they are notoriously difficult to detect and confirm. How many more are out there, masquerading as ordinary stars in our catalogs and our night sky? Every seemingly simple sun could be a crowded celestial empire, its story silent until the next generation of telescopes listens more closely. This theoretical limit of stability is a frontier explored not with telescopes but with pure mathematics. Astronomers use supercomputers to run countless simulations, creating virtual universes to test the absolute boundaries of gravitational harmony. These digital experiments paint a clear and startling picture. While a sextuple system can achieve a delicate, lasting balance, adding just one more star pushes the entire configuration toward almost certain chaos. Systems with 7 or even 8 stars are not just rare, they are exponentially more fragile. The gravitational interactions become too complex, the potential for close encounters too great. A stable hierarchy becomes nearly impossible to maintain over billions of years. The inevitable outcome is a violent scattering, a gravitational slingshot that ejects one or more stars into the void, simplifying the system back to a lower, more stable order. This points to a profound cosmic discovery. Sextuple systems may represent a natural sweet spot, the highest order of complex stellar multiplicity that the universe can routinely build and sustain. They exist at the very precipice of gravitational possibility. This theoretical finding transforms our understanding of the systems we have already found. They are not merely statistical flukes. They are the ultimate expression of stable complexity, the most crowded and intricate neighborhoods that cosmic physics allows to endure. Their enduring dance is a testament to a perfect, natural balance between chaos and order, making each one a precious laboratory for studying the fundamental laws that govern all stars. What other universal rules are written into the delicate architecture of these 6 sun families? V994 Scorpii offers a masterclass in celestial order. This system, one of the very first confirmed with not 1 but 3 eclipsing binary pairs, presents a configuration of such clockwork precision it defies its own complexity. Its 6 stars are arranged in a pair of pairs with a third binary locked in a wider orbit around them. From our vantage point on Earth, we are perfectly positioned to watch each of these 3 pairs perform its own eclipse, with one star of the duo passing directly in front of the other. The result is a light curve of breathtaking clarity. Instead of the tangled, chaotic scribble you might expect from 6 stars, the graph of its changing brightness is a sequence of deep, clean dips, a rhythmic pattern that repeats with the reliability of a metronome. Each dip is a perfect shadow cast as one star precisely blocks its partner. This pristine predictability transforms V994 Scorpii into a perfect natural laboratory. Because the eclipses are so clean and well separated, astronomers can measure the exact depth and duration of each dimming event with incredible accuracy. From these precise measurements, they can derive the exact sizes, masses, and temperatures of all 6 stars with a level of detail that is nearly impossible to achieve in any other way. It is as if the stars themselves are holding up calibrated rulers for us to read. The profound strangeness of this system is not its chaos but its order. V994 Scorpii single-handedly proved to the astronomical community that a family of 6 suns was not just a theoretical possibility or a fleeting cosmic accident. It demonstrated that such high multiplicity systems could achieve a state of enduring gravitational harmony, and more importantly, that they could be perfectly transparent to our methods of study. This one system opened the door, proving that the most crowded stellar neighborhoods could also be the most revealing. These ancient families of 6 suns are more than just stellar curiosities. They are cosmic time capsules carrying within their orbits and their very atoms a pristine record of the galaxy's violent infancy. To find them, astronomers look not in the bright, crowded disk of the Milky Way, but in the sparse and ancient halo that surrounds it. This vast spherical cloud of stars is the galaxy's archaeological dig site, home to the oldest stellar populations. A sextuple system discovered here is a fossil, a relic that formed when the universe was young and the proto-galaxy was a dense, tumultuous place. Its continued existence is a miracle of stability. For a system of 6 stars to survive for 10 billion years or more, it had to endure a gauntlet of gravitational threats. It had to drift through crowded star clusters without being torn apart by a close encounter. It had to navigate the chaotic mergers of smaller galaxies that built our Milky Way, all while maintaining its delicate internal balance. The fact that we find any at all in the halo is a testament to their incredible toughness. Their chemical composition tells a story no single star ever could. The specific mix of elements in their atmospheres, elements like iron, carbon, and oxygen, acts as a timestamp. It reveals the composition of the primordial gas cloud from which they were born, a cloud that had been seeded with the heavy elements from only the very first generations of supernova. By reading this chemical fingerprint across all 6 members, astronomers can reconstruct the environment of that long-vanished stellar nursery. But the most profound record is written in their motion. The precise orbits of a halo sextuple system preserve a memory of the gravitational forces it experienced billions of years ago. Its path through the galaxy today is like a final footprint, but its internal dance is a clock that has been ticking since the beginning. Any slight warping or precession in its orbital planes could be the lasting imprint of a close brush with a massive dark matter clump or a dwarf galaxy that was consumed by the Milky Way eons ago. These systems are not just passive relics, they are active witnesses, their 6-fold harmony a continuous song that has been playing since the cosmic dawn, holding secrets about the forces that sculpted our galactic home. What other chapters of our galaxy's forgotten history are locked within the enduring dance of these ancient stellar families? Standing on the surface of a world nestled within a sextuple system, your very perception of day and night would be utterly rewritten. The sky is not a dome with one dominant light, but a dynamic canvas where several suns drift in a slow, perpetual ballet. Their colors are a discordant palette, a brilliant white star sharing the heavens with a sullen red and a warm orange giant. Their movements are not the simple arc of our sun, but complex, interweaving paths governed by the intricate gravitational chords of their dance. Your shadow is not a single, defined silhouette. It is a fractured, ghostly thing, a fan of faint, overlapping penumbras cast by the different suns, each pointing in a different direction as if you were standing at the center of a cosmic sundial. There would be no true night, only a shifting scale of twilight. As one star sets, another might be rising, while a third hangs perpetually at the horizon, bathing the landscape in eternal, eerie dusk. True deep darkness would be a mythical concept, a condition this world might never experience. The most breathtaking spectacle would be a sunset, but not as we know it. Instead of a single star dipping below the horizon, you might witness a cascade of them. First, the white star vanishes, its harsh light fading to reveal the softer glow of its companions. Then the orange star follows, leaving the dim red sun alone in the sky, casting the world in a deep, blood-red gloom for a few hours before it too begins to rise, chased by the returning white star. This constant celestial motion forces a profound philosophical shift. For any intelligence that evolved under 6 suns, the concept of a solitary star would be the truly alien one. Our own peaceful, predictable sky with its single yellow sun would seem to them an impossibly lonely and barren place. The discovery here is not about orbital mechanics, but about perspective. Our sun-centered existence is not the universal standard, it is a cosmic outlier. In the grand tapestry of the galaxy, the norm might very well be a sky filled with multiple wandering lights, and the quiet solitude of our own solar system is the real celestial anomaly. A star's heartbeat often first flickers onto a screen not in a professional observatory, but in a home office halfway around the world. The crucial first alert for many of these bizarre 6-star systems has come from a global network of dedicated amateurs and citizen scientists, people who study the sky for the sheer love of discovery. For generations, these observers have meticulously tracked variable stars, noting the ones whose light curves defied all simple explanation. A pattern of dips that should have belonged to a single eclipsing binary would be complicated by secondary, overlapping shadows, hinting at the presence of additional, unseen dancers in the celestial ballet. These strange, complex signatures were the first clues, handwritten in notebooks and shared in community bulletins, that prompted the deep, professional investigations that ultimately revealed the full sextuple truth. In our modern era, this human-powered discovery process has scaled to incredible heights. Space telescopes like TESS and Kepler do not take pretty pictures. They generate colossal rivers of raw data, millions upon millions of light curves from stars across the sky. No single team of professional astronomers could possibly sift through it all. This is where the global community steps in. Through online citizen science platforms, hundreds of thousands of volunteers examine these graphs, classifying patterns by eye, their collective intuition often spotting the subtle, tangled rhythms that automated algorithms might miss. They are the first to flag a star that winks with a convoluted signature of 3 separate eclipsing binaries, a telltale fingerprint of a system like TIC 168789840. This collaborative filtering is invaluable, turning an overwhelming flood of data into a shortlist of high-priority, profoundly strange candidates for the big telescopes to target. This partnership proves that the most advanced tools of science are made infinitely more powerful when paired with human curiosity. Every time a volunteer clicks on a strange light curve, they are not just processing data, they are peering into the heart of a distant stellar family, joining a timeless human quest for understanding that connects the backyard stargazer to the most powerful observatory on Earth. Our final strange discovery is not about the past, but about a future that is rapidly approaching. The next generation of astronomical giants is poised to tear away the final veils from these 6-star families. The James Webb Space Telescope, with its infrared eyes, can peer through the obscuring dust of stellar nurseries to witness the raw, chaotic birth of new sextuple systems in real time. But the true revolution in resolution will come from the ground. The extremely large telescope, with a mirror nearly the size of a blue whale, will possess a stunning new power. For the wider systems, it will not just infer the presence of stars through their wobbles and shadows, it will directly split the light, resolving individual stars within a binary pair that orbits another binary. We will have a portrait of the entire family, a detailed image of their cosmic dance. This leap in clarity will transform every shadow in a light curve into a known, visible object. We will watch as the gravitational tides from one pair warp the protoplanetary disk around another, witnessing planet formation in the most extreme environment imaginable. The atmospheres of any surviving planets will be analyzed for biosignatures, answering the profound question of whether life could take root in a sky with 6 suns. Perhaps the most thrilling prospect is the chance to catch a system in a moment of instability. We might witness a close gravitational encounter that subtly rearranges the orbits, or even spot the faint runaway star just as it is ejected, watching a family break apart in an event that unfolded over mere decades instead of millennia. The ultimate strangeness, the final discovery that ties all 25 together, is the humbling realization that we are only at the very beginning of this story. The systems we have found so far are the obvious ones, the loudest and brightest members of a population that is likely far larger and more bizarre. The true nature of stellar multiplicity, the full range of gravitational harmony and chaos, is still waiting in the dark, ready to be revealed by the next generation of tools and the next generation of curious minds